One important use for trig functions is vector analysis. Lots of engineering parameters are represented by vectors. Vector analysis often involves transformations between polar and rectangular coordinate systems, which invariably involves trigonometric functions. Before I talk about analyzing vectors, I'll review what vectors are and introduce some notation about them. Vectors model parameters that have both magnitude and direction. Displacement, velocity, acceleration, and force are all examples of vector quantities. Scalar quantities, on the other hand, have only magnitudes and are completely described by a single number. Mass, volume, density, and charge are all scalar quantities. Graphically, vectors are denoted by an arrow. The direction of the arrow indicates the direction of the vector, and its length usually provides an indication of its magnitude. In symbolic math expressions, vector quantities are usually indicated in boldface type or with either an arrow over the variable or a bar under it. A bold V, a V with an arrow over it, or a V with a bar under it would all represent vectors. Vectors can be represented in any valid coordinate system. In this course, we'll use either polar coordinates or rectangular coordinates. Polar coordinates provide a magnitude of the vector and an angle from some reference direction. The positive x-axis is a common reference direction. In rectangular form, the vector is represented as components in the x and y directions. The two directions are indicated with unit vectors x hat and y hat. X hat is a vector with length of 1 in the purely x direction, and y hat has a length of 1 in a purely y direction. There are lots of mathematical relationships involving vectors, but in this video I'll focus on addition. I'm going to add two vectors, v1 and v2, to get a vector v3. v1 will be represented as a red arrow and v2 as a blue arrow. There are a couple of approaches towards vector addition. The first one I'll talk about is called the polygon rule. In this course, we'll only deal with what are called free vectors. This type of vector can be moved around in space without changing its effect. In this case, we can move the vectors around so that they are placed tip to tail. The sum of the vectors is simply a vector that points from the tail of the first vector to the tip of the second. It doesn't matter which vector you place where. Putting vector v1 at the tip of v2 results in the same thing as placing v2 at the tip of v1. The disadvantage of this approach is that the arithmetic gets tedious when dealing with a large number of vectors. As an example of the polygon rule, let's look at the case of a boat crossing a river. The water velocity in the river is 5 kilometers per hour, and the boat travels at a speed of 10 kilometers per hour relative to the water. We want to know what bearing, the angle theta, results in the boat going directly across the river. If we look at the vectors involved, we get a triangle that looks like this. We know both the magnitude and direction of the water velocity. It has a magnitude of 5 and it's directly parallel to the shore. We also know the magnitude of the boat velocity, 10 kilometers per hour, but not its direction. Finally, we know the direction of the desired velocity. We want to move perpendicularly to the shore, but not its magnitude, since we don't care how fast we're moving in that direction. We want to find the angle theta that makes us move perpendicularly to the shore. Since this polygon is a right triangle, the math is pretty easy. The length of the side opposite to theta is 5, and the length of the hypotenuse is 10. The sine of theta is the opposite over the hypotenuse, which is 1/2. And the inverse sine of 1/2 is theta, which is 30 degrees. Now let's change our problem just a little bit and see what happens. We're now heading our boat directly toward a beach at a speed of 10 kilometers per hour. The water is moving at a 45-degree angle to the shore at a speed of 5 kilometers per hour. We want to find the actual direction, theta, of the boat's motion. Now our vector triangle looks like this. The triangle doesn't have any right angles now, which means we can't use our basic trig functions to analyze it. There are specialized functions we can use to solve this problem, but there is a more universal way to approach it. We'll look at that next. Our fundamental problem hasn't changed. We still have two vectors, v1 and v2, that we want to add together. This time, however, we'll break the vectors down into x and y components. After we've determined the x and y components, we'll add the components in each direction individually. If we decompose both of these vectors into x, y components of a rectangular coordinate system, we end up with these four vectors, which are equivalent to our original two vectors. Then the x component of the vector v3 is the sum of the x components of v1 and v2. Likewise, the y component of v3 is the sum of the y components of v1 and v2. Finally, the vector v3 is just the sum of the individual x and y components of v3. Let's see how this approach applies to our boat example. We still want to find the direction of the boat's motion if its heading is directly towards shore at a velocity of 10 kilometers per hour and there's a 5 kilometer per hour current at an angle of 45 degrees to the shore. The directions and magnitudes of the vectors involved are shown here. In order to project the vectors onto a coordinate system, we first need to define the coordinate system we're using. I'll choose an xy coordinate system with the x direction being parallel to shore and the y direction perpendicular to that. Now we can project these vectors into components in these two directions. VB, velocity of the boat relative to the water, is purely in the y direction, so it becomes 10 times y hat. The velocity of the water is at 45 degrees to shore, so it has an x component of 5 times cosine of 45 degrees and a y component of 5 times the sine of 45 degrees. The total velocity vector v is the sum of these two velocity vectors. The components add independently, so the total velocity is this. The only x component is 5 times the cosine of 45 degrees. The y component is the sum of this y component and 10. We want the angle theta, so we need to convert this to polar form. The angle is the arctangent of the y component over the x component. 5 times cosine of 45 degrees is 3.54. 5 times sine of 45 degrees is also 3.54, so this becomes 13.54. The arctangent of this divided by this is about 75.8 degrees. The really nice part about this approach is that decomposition of the vectors into orthogonal components works fairly easily for a wide variety of problems. We can handle addition of a large number of vectors with the same tools as we use for just these two vectors. Another common situation where transformations between polar and rectangular coordinates occurs is in complex arithmetic. I'll talk about complex numbers and representing them in different coordinate systems in the next video.